invitation to speak. So a pretty large number of the audience here maybe remembers a talk I gave 2 years ago in Rio, which was sort of the start of a project of extending Floer chromology and Fukaya categories to, well, stable generalized complex structures or log symplectic structures. And so this is another of those, although I'll be coming at it from a different angle today. So basically, what I'm going to do today is sort of pretty concrete, because I'm going to be doing it on real surfaces, so real log symplectic surfaces. Of course, there are no terribly interesting generalized complex structures on real surfaces, but because the dimension is so low, a lot of the difficulties with Floer chromology and Fukaya categories go away, and so surfaces are a nice sort of initial step to get a bit of an idea of what's going on. So first of all, what approximately is a Fukaya category? So the idea is to associate an A infinity category to a symplectic manifold, and this is frequently used in the context of homological mirror symmetry, where you then want to compare this A infinity category to an A infinity category associated to the complex structure on a different manifold. So in general, you have a symplectic manifold, and to make it easy, it should be compact, and symplectically is aspherical. So that means that integrating the symplectic form over two spheres always vanishes. So as the objects, you want to take some collection of compact Lagrangian submanifolds up to Hamiltonian isotropy. And as the morphisms, so this is generally written as the Floer chain or co-chain complex. You want to take the span of intersection points of the two Lagrangians over some field. So in the general case, it will be what's called a Novikov field. Here in my talk, it will always just be Z2, because that's easiest. And since I said we want to count intersection points, we better have that the two Lagrangians intersect transversely, so that there's actually a finite collection of intersection points to sum over. So in addition, an A infinity category always comes with this collection of A infinity operations. So for every natural number, there's one of these, and this is actually an extension of the composition of morphisms. So these go between the Hom spaces. Like this. And these satisfy some relations, A infinity relations. So more explicitly, what are these for small k? So mu1 this will just go from one Hom space to itself. And the A infinity relation here is that this squares to 0, so it's a differential. And mu2, which will take 2 arguments, this is a composition of morphisms. So it will take an element in Hom of L1 to L2 together with Hom L0, L1 and result in one from L0 to L2. However, so this is not, what makes this not a category is that in general this composition is not associative, and so it's merely associative up to terms that involve mu3 and mu1. So yeah, this is how these higher relation or these higher maps come about, that the essentially failure of associativity up to these higher terms. However, if we take the chromology with respect to mu1, so the differential, then we use that as morphisms, then we would get an honest category with associativity. So in this context, I'm going to mainly talk about how to define mu1, although the higher ones follow the same principle essentially. So this is the Floer differential. In general, what one wants to do is consider maps from a strip like this into the manifold, such that the lower boundary of the strip lies in the first Lagrangian and the upper boundary lies in the second one, and the ends of the strip, so the end at infinity and at minus infinity, are precisely 2 intersection points of the 2 Lagrangians. So that looks like this. Here are the 2 Lagrangians, they intersect in 2 points, and then this strip is going to go in the middle. And these maps have to be holomorphic or pseudo-holomorphic, so they satisfy Floer's equation, which looks like this. So this is a modified Cauchy-Riemann equation, essentially. This JT here is we take to be an almost complex structure that's compatible with the symplectic form, and we allow it to vary over this parameter t. And then here we have a Hamiltonian vector field for some time-dependent Hamiltonian HT. And that is necessary because the Lagrangians might a priori not be transverse, so then we can perturb them with a Hamiltonian isotropy to make them so. And now we use spaces of these kinds of maps to actually define the differential. Like this. So del of an intersection point P is the sum over other intersection points of the same Lagrangians potentially perturbed by Hamiltonian isotropy, and over such maps or homotopy classes of such maps U that are of a certain index. I'm not going to say what the index is, but that has to do with the dimension of the moduli spaces of such maps. And then we count these pseudo-holomorphic strips in a given homotopy class. And we have that as the coefficient in front of the intersection point Q. So here's a factor with a formal parameter T that scales with the area of the pseudo-holomorphic curve. So in general, you put this in because there might in total be infinitely many, but only finitely many of a certain volume. So this is the moduli space of these pseudo-holomorphic curves after parameterizations. And now, given the right conditions on the manifold and the Lagrangians, this is actually a differential. But so in general, it won't be. So these conditions are somehow genuine conditions. Now, the cohomology with respect to this differential is Lagrangian intersection cohomology. And so, yeah, that was first introduced by Fleur. And while the chain complex, of course, depends on all the choices we have made, the cohomology is a genuine invariant of the two Lagrangians. So that does not. In particular, it doesn't depend on moving one of the Lagrangians with a Hamiltonian isotropy. And since this is so, it makes sense to also define the Fleur cohomology of a single Lagrangian, which is then that of the Lagrangian and a perturbed version, so that they intersect transversely. And famous theorem by Fleur is that this is the same as the singular cohomology of the Lagrangian. So in this way, it fits together with what was already known. So in describing the theory like this, I have left out a great number of analysis difficulties. So in order to really do this, one has to be very careful with all sorts of details, so of an analytical nature. But if one restricts to symplectic surfaces, so orientable surfaces, then really all these analysis details go away, so that those issues don't arise anymore, and the theory becomes purely combinatorial. So this is relatively well known. So there's a monograph of De Silva, Leuven, Salomon laying out this combinatorial for cohomology for symplectic surfaces. There's also work by Abu Zaid on the Fukaya category of higher genus surfaces, and Fuller for non-compact surfaces. So what does this reduce to if we have a symplectic surface? So two-dimensional. The Lagrangians are simply, well, one-dimensional submanifolds, right? Any one-dimensional submanifolds will be Lagrangian. And so what we want to take here are embedded circles that are not contractible. So I have to restrict in order to non-contractible circles, because if I have circles that you can fill in with a disk, then the Fleur differential just won't square to zero. So only ones that are not contractible. And to start with, we also don't want them to be isotopic to each other and to intersect transversely. And then these pseudo-holomorphic strips are really just, well, these sort of what these authors refer to as smooth loons. So these kinds of half moon shaped shapes that you can just actually see in a picture. So this is alpha, this is beta, this is P, this is Q. These should have convex corners. That essentially amounts to this index requirement that I had in the general definition here. But then we call this a smooth loon from P to Q. And we define the differential just using that. So del T is...
Sorry, what does it mean, convex corner?
What
is a non-convex corner?
Sort of this. So the angle of the corners, so asymptotically, should be a maximum of 90 degrees. Sorry, a maximum of 90 or 180 degrees. 90.
I don't understand also the drawing of a non-convex. What?
So, if if I have this sort of thing, so this is alpha and this is beta, then this would not be a loon between these 2 points because this angle is too big.
So, but then beta doesn't look like an embedded. Well, I don't know how it continues.
Okay, but I mean, I could continue it like this, right? And then I could still ask about loons between these 2 intersection points.
But do you also have a metric around? Or?
So, right now it's not important. I mean, I have a symplectic form.
No, I was thinking to calculate these angles.
Oh, so this can actually be done purely combinatorially. I'm just saying it like this so you have an easy picture of what these should look like. But if you want to formally define this, there's a way of assigning a combinatorial index to these kinds of shapes. And what I'm saying is, again, the combinatorial index that gets assigned to this should be 1. I've drawn it this way so you have sort of an idea of what kind of shapes you would be looking for when doing this. Because
there's an almost complex structure which is defined in order to define this equation, and that almost complex structure gives you a conformal structure at the point.
All that, yeah. Okay, where was I? I was writing down the equation. So in this case, the expression for the differential is simple. So this is then the number of smooth loons between the 2 points. And we are working over Z2, so this is, well, either 0 if there are none, or it's even, or it's 1. And so in this context, this will square to 0, although I will not show the proof in the interest of time. And instead go to talk about orientable log symplectic surfaces. So these were classified as topologically stable Poisson structures by Olga Rasto. So we assume we have a bivector on a surface. Every bivector is of course Poisson, but those that are topologically stable or log symplectic are those that intersect 0 transversely. So this means in particular that the locus where the Poisson structure vanishes, which I'm going to call Z, is a collection of embedded circles that are disjoint. So what this always looks like locally around such a vanishing circle, so here's that, there's always a normal form around these that looks like this. Where the coordinates are chosen so that the modular vector field of the structure restricted to this connected component of Z is this delta theta, and then this will be a positive real constant. And note that the restriction of the modular vector field of the Poisson structure always gives an orientation for each of these circles. So as soon as we have chosen a pi, yeah, the orientation is fixed. Come on. Right, and so we can view this as a log symplectic structure by taking the inverse. And then that looks like this in local coordinates. So the theorem by Radko for the classification says that these are classified up to orientation preserving Poisson isomorphism. By essentially three things. So the collection of the ZIs up to orientation preserving diffeomorphism with orientation. So this is the class. Modular periods, which come from basically integrating the modular vector field around the vanishing cycle, so that's where this constant C comes in. So these kind of periods, and what's called the regularized Leuven volume, which is basically the integral of the log symplectic form over the surface, which of course naively isn't defined because the symplectic form goes up, but it turns out that in the compact case the infinity components cancel each other out, and there is actually a regularized finite version of this. Now, when extending the definition of a Fukaya category to log symplectic surfaces, one expects that these kinds of invariants would somehow manifest in some way in that Fukaya category. And I'm going to give you a little bit of an idea of how that would work. And I'm going to show you how to define log homology in the log symplectic case. log symplectic surfaces that I'll look at are the sphere with one vanishing locus at the equator, if you want, and the disk, where the boundary is the vanishing locus. And of course, you can think of this log symplectic disk being the upper hemisphere of the log symplectic sphere. So this is what these coordinates look like. Construction. Okay, so now if we want to plot this
sorry, this bivector which is equal to the two form.
I should have written the form here. Yeah, sorry. Like this.
And then on the right hand side, is it also 1/2?
Yes. Thanks. There we go. Yeah, so what's different from just the symplectic surface case? Well, it's of course mainly what happens where the Lagrangians intersect the degeneracy locus and what that does. So essentially what we can immediately notice is that Hamiltonian isotropies, so for any function, the Hamiltonian isotropy, when restricted to the vanishing locus, is the identity. So we can never move intersections of Lagrangians with the degeneracy locus around. These will always stay the same. And so in particular, you can already see that the notion of what Lagrangians get identified as the same object in the Fukaya category, that changes because, well, if this was just symplectic, I would have much more freedom in moving Lagrangians into each other, whereas here the intersection points with Z always stay fixed. And I guess it's sort of an idea. So one of the invariants associated to a log symplectic surface is this modular period. And so I think that the intersection points of the Lagrangians being fixed should somehow be a reflection of, you having, if you want, Lagrangians for each intersection point with Z. So that's where somehow the modular invariant would go in this categorical picture. And so when we just look at the disk,
couldn't you just move them using the modular vector fields, which are Poisson but not Hamiltonian?
Yeah, but I think you should only identify things that are related by Hamiltonian isotropy, just as in the symplectic case. You wouldn't use general symplectic vector fields either. So there's those should be different objects. Okay, so with the disk, we still want the Lagrangians to be non-contractible, so in particular these should just be intervals that somehow go between 2 points in Z, and they can intersect in various ways, and what we want to find is for our definition of Floer chromology to be invariant under isotropies with these fixed endpoints. And in the case, the first case, where the two Lagrangians intersect, but not inside Z, this turns out to be pretty simple. So the definition of Floer chromology that we had in that case goes through with just the adaptation that, the endpoints should stay fixed. So in particular, you will, so you don't see this in the disk, but you can see this in the sphere. If these are two Lagrangians, and this is Z, there will be no loops that go through Z like this. And that's basically because if you take the analog of the Floer equation, adapt it to this context, yeah, well, there can be no solutions that sort of genuinely pass through Z in this way. And so, yeah, we essentially just port the theory from over there to here. Now, where it gets more complicated is when the two Lagrangians actually have intersection points inside Z. So in particular, this is the case we need to look at if we want to define the Floer chromology of a Lagrangian with itself, right? Because if we move the Lagrangian with any Hamiltonian isotropy, the intersection points with Z will be the same. And so the image under any Hamiltonian isotropy and the original Lagrangian will always intersect inside Z. So case 2. So examples. Doing this, or as I just said, if we have a Lagrangian alpha and we just perturb that with an isotropy, we could have these sorts of things. And with this naive, so first of all, there's one new thing that we didn't have before, and that is these kinds of loons that end in Z. So the question is, what about those? And then there's an additional issue which you can see, which comes from us so far allowing all Hamiltonian isotropies to perturb the Lagrangians. Namely that, so under that picture, these would be isotropic, right? So the Floer cohomology that we define using these two pictures should be the same, or isomorphic. But, and in particular, like any other thing that we do, like this. And if you think about this for a second, it won't be. So these will not be the same. So clearly, just allowing any sort of Hamiltonian isotropy in this context will not work. Instead, what we do is, so for this to work, we need to assume that we've chosen an orientation for M. So I was assuming that so far that we're only working on orientable surfaces. And then I already mentioned we have this canonical orientation of Z coming from the modular vector field. And so let me see how I had defined the coordinates. So this is theta, and this is x according to these orientations. Then what we want to do is only use Hamiltonian isotropies where near the boundary or near Z, the Hamiltonian is of this form. So f times x, where f is a positive function. So that just needs to be through some neighborhood near the boundary. And so what this amounts to is saying that what we can do, I'm going to use a different color, is always, so near the boundary, moving a Lagrangian, let's say with the form beta now, so moving it this way. And then in the middle it can do whatever. And then we set the plane complex, or the Hom space between them, to be alpha and the perturbed version of beta, where phi so the phi is now the flow of such a Hamiltonian. What you will see from this picture that I drew on the left is that this now makes the Hom spaces not be symmetric,
Sorry, I have a question. There, you said that you wanted the flow to keep fixed Z, right? It was written there. Now it's not the case.
No, it is.
Z is the boundary of the.
That is the boundary where x is 0. So the Hamiltonian.
X starts there. Sorry,
Yeah,
I
sorry,
thought it
yeah,
was
yeah.
the radius.
No, x starts on
Okay,
on the boundary.
thank you.
Okay, so if we again look at this picture on the left, with the two Lagrangians that intersect in one point in Z, and the other two intersection points are separate. So what we find is that in order to define the f of alpha beta, we should use this picture and the intersection points in this picture, whereas for the other one, so Cf beta alpha, that will now be something like this. Or if you want, so these are equivalent. And now with this modification, we can restore the invariance under Hamiltonian isotropy, where now Hamiltonian isotropy is just with with these kinds of Hamiltonians. And so that kind of thing is not unprecedented. So when you do this when you do Floer chromology for symplectic manifolds, and you have non-compact manifolds, then you usually also need to specify what the Lagrangian does as you go out towards infinity. And so that is basically an analog of this kind of thing. And so now we also see that when we want to define the Floer complex for a Lagrangian with itself, the kind of perturbation we need to do is this. Or, I mean, with more wiggles in the middle, that's always allowed.
So then what you are suggesting is that you are treating the log symplectic as a symplectic manifold with punctures at infinity or something like that?
Well, not exactly, because I mean, if you want to, a little bit, but not exactly, because I'm explicitly keeping the boundary in and making sure that everything is fixed at the boundary. And I think that's important, that sort of the invariants of the Lagrangians are genuinely the intersection points with where they hit infinity, if you want. And also, this is a special case, of course, because the boundary has a trivial Poisson structure, right? The restriction of the Poisson structure to Z is trivial, and so nothing much interesting happens in there. But if you now want to go into higher dimensions, then, there would be non-trivial things going on in the degeneracy locus as well. So you definitely don't want to remove that entirely. Okay, so now the question, or a question that's left, is sort of what about these kinds of things? Should there be loons here? And the answer in this case is no, there shouldn't be. So, like this. So if we have a loon like this from a point Q, or from a point P to a point Q, so this is not a loon. And essentially the rationale behind this from the pseudo-holomorphic curve perspective is that the volume or the area of this would be infinite because it blows up as it approaches the degeneracy locus. And so that should not be included. And well, then you can go and define a Fukaya a Floer chromology for this context on the disk. Yeah, with these sorts of rules, and that will be invariant under these kinds of Hamiltonian isotropies. So there's one more thing. So far, I've only discussed the disk, where the degeneracy locus is the boundary. But now, as the sort of last thing, how much time do I have left? Oh, okay, should be enough. I want to discuss the sphere, where we actually have two symplectic components that sit on both sides of the degeneracy locus. And there is a new phenomenon that we haven't yet seen. So here's S2. Here's that. The Lagrangian alpha, that is also, I mean, if you want, that is also just one of the big circles. And now we want to look at the Floer cohomology of alpha with itself. So let's put in the sort of coordinates that we had. So this is theta, this is x, and so here theta is in this direction, x. So now we perturb the Lagrangian according to the rules we had. So around here it gets perturbed like this, and around here like this. Then we join these up. Like this. So we have 4 intersection points, which I'm going to call Q1, Q2. Those are the ones that are inside that Z. And P1, P2, the ones outside. Okay, so according to what we've learned from just looking at the disk, well, we know that we shouldn't have loons that start or end in the Q's. So del Qi is just 0. And so there's also no loon from P1 and P2 to Q1 or Q2, so these will also not be in the image. However, what you can now see is that we have this kind of broken loop that looks like this. So if I draw that again here, I should draw it the other way around. Actually, I have 2 of those, right? So one on the front and one on the back of the sphere. And so this we should now take into account as a loon going from P1 to P2. And again, with the argument of the sort of pseudo-holomorphic picture, why is this now okay? Because if we take the area over this entire thing, the components that blow up will cancel each other out because the log symplectic form has different signs on both sides of Z. So this will actually be a loon with a finite volume. And so we should take that into account. Yes?
Can I ask you something? In this differential equation, one would expect that the velocity when you reach Z goes to 0.
Yeah.
Is that the case?
Yeah. So it can be just a sort of corner thing.
Right. So it reaches 0 and then it continues afterwards.
Yeah, so if you want, it reaches 0 from both sides somehow, but yeah, it's a velocity 0 at the...
And this contributes to this vanishing that you're saying, or is this just because of the...
Contributes to the vanishing in what?
Sorry, not but the cancellation that you were mentioning.
Oh, I mean, it's mainly just that the symplectic form, oh, I've erased it, so I'm just going to write it again. So here, this is x equals 0. And the symplectic form is something like this. And so here we get, this pole, but on this side, x is positive, and on this side, x is negative. So if I integrate these, the sort of blowing up bits cancel out. Right, and so this example, if you want this example that I've drawn here of the Lagrangians is still not super exciting, but I'm going to write it down anyway, because the differential is still trivial. So if we go from P1, are 2 looms to P2, so this is actually still just 0. Del P2 is also 0. And
sorry, does it mean that these symplectic areas, they are all 0 in total? Or what?
No, so I'm working over Z2, and I'm not taking symplectic areas into account for the definition of the Floer differential, because in this case it works without doing it. So as soon as I go to a more complicated situation, like for example a cylinder where both ends are degeneracy loci, then I would also have to have Lagrangians that are circles around the circle of the cylinder, right? And as soon as I start doing that, the Floer differential will only be well defined if I put in this scaling factor with the area. But for this, it's sort of, this is the easiest case where it works without. Okay, so here what we find is that the Floer cohomology of this circle with 2 intersections with the degeneracy locus is, well, Z2 to the 4, but I want to write that as Z2 to the 1 plus Z2 to the 3. So, because I now want to compare this Floer cohomology to the cohomology of the circle as a Lagrangian as we already know it. So, this is the circle with 2 marked points on it. So, in particular, the natural cohomology associated to this is the log cohomology of the circle. So, log cohomology with respect to its intersection locus with Z. And the zeroth degree, this is also just one-dimensional because it's still a connected thing. And then in the first degree, it is r to the 3, and that comes from the first order cycle of the circle, in the first degree, and then the 2 connected components of alpha intersect Z. And so what we see is that, if I did these over the right kind of rings, these are actually the same. So this kind of Floer cohomology precisely gives you back for a single Lagrangian the log cohomology that you would expect. And so then somehow from this picture we can also say that it sort of if we wanted to do this graded. So I've only done it over Z2, but it is possible to do this in a graded way. So where you assign a Z grading to the intersection points. And so in this case, what this should be is this. So we should somehow have 3 intersection points sitting in degree 1 and 1 in degree 0. Okay, so as the sort of last thing, I'm just going to say a few things about how to continue from here. So first of all, the higher A-infinity maps, which involve, so instead of involving these looms, they involve polygons with more intersection points in the corners. And that also works fine with the same restriction on Hamiltonian isotropies that we've already put in here. So with this, one can sort of go and build up the entire A-infinity structure. And then there's, of course, the question, well, what happens with more complicated log symplectic surfaces? So to start with, one could start inserting more degeneracy loci into the sphere, for example. And so component-wise, you could always, if you just look at sort of the single symplectic components, these will always be S2 with n punctures, where each puncture has a circle that is a degeneracy locus, so higher and higher genus. And when you put them back together, you would have to start considering loons that are broken by multiple degeneracy loci. And so this stuff I haven't worked out formally, but I think you would just continue the same way. So you would want to pay attention to all the broken loons that go through the different numbers of degeneracy loci. And so using these same principles, it should be possible to build up this theory for all orientable log symplectic surfaces. Yeah, thank you for your attention.
So I'm just curious, so you were focusing in this computation on a circle, like an embedded compact submanifold.
Yeah.
You're not proposing to have these chords with boundary on Z as being objects, is that right?
No, right now I'm not, yeah.
What do you think the objects are? So these
No,
are
I think the objects are embedded circles at the moment,
okay.
yeah.
And the location of the intersections, right? You were explaining how you know that is a parameter in the category. So does that mean that there's like a whole moduli space of objects of this type, of these circles, parameterized by points on the circle?
Yeah, that are not equivalent, yeah.
So can they be compared? Can you compute Hams from a circle? Let's say you were to rotate that circle about the axis, right? So that it would intersect in a different location. Would it make sense to take Ham from the first circle to the second circle?
Well, yeah, because they'd intersect outside Z. So then the Ham would just be the intersection points that are outside Z, which was the simpler case I started with.
Okay.
So if I remember, in the case of standard symplectic space, R2n, I think you can do for homology where you take compactly supported Hamiltonians that are positive.
Yeah, maybe that's that.
So I was wondering if you thought about how does this connect, where you would take now compactly Hamiltonians which are supported outside Z, and which are positive or negative depending on the sign that you have on each.
Basically be that.
It would be that, something very similar to what you have, no?
Yeah. No, it would be, yeah, so I guess in that sense it is true that you could, I guess from this you could go back to just the non-compact case by removing Z, and then, so if you look here, so this is basically that, right? Like if I remove the case where X is 0, then I'd either have a positive Hamiltonian, or on the other side of Z, I'd have a negative Hamiltonian, which, I mean, is if Z lies somewhere in the middle. Yeah, so like if you want, you can somehow go back from, go from this to just the non-compact case. But as I've been saying, so.
But would that, do you think that would extend to higher dimensions?
Yes, so as soon as you go to higher dimensions, there's a whole host of issues that I mentioned earlier with this.
Right, but because in this way you are like, you know, what happens outside Z controls what happens in Z asymptotically.
Yes,
so in this way you would be like hiding that.
Yeah, so example one thing that I haven't mentioned is sort of what about things that are entirely inside Z? And so I think, so in higher dimensions certainly there would be objects that are entirely contained in Z. In this dimension, I think that possibly Z itself should be an object also. So somehow by removing that, you'd actually removing an actual thing. So yeah, I think that somehow the circle Z should be an object.
Or even the points on Z.
Yeah, although I guess so if you want a one-dimensional.
I mean, I'm just thinking that the co-isotropics
Yeah.
would be objects.
Yeah, okay, yeah. Yeah, then the points in Z.
Any more questions? Are there any online questions or? So then, well, let's thank Charlotte again.